much, and I am once again happy to have had the invitation to give these lectures. Thank you to KIAS. I'm glad to help celebrate your quadrant centennial. So I'm going to start in the first few minutes by just reviewing the logic, not the details, about the generalized second law. And then we'll move on to discuss the fine-grained entropy. So here again is the Penrose diagram of a black hole. The red is a star that eventually collapsed to a black hole. And this diagonal black line is the horizon. And then we made a cut of the horizon right here, and we connected that cut to spatial infinity on a space-like hypersurface. And then we defined the generalized entropy on that cut. It's the area over 4g times h bar, plus the entropy outside the cut, which by now we've learned is the von Neumann entropy outside the cut. Now we could make a similar cut at a later time. And the generalized second law says that the generalized entropy is greater on the later cut. Now, I'm going to just briefly review the logic in the proof of the generalized second law. Now, I think I might have slightly confused people with the explanation of what's the geometry of the horizon. So let's just look at this picture for a spherically symmetric black hole. And the horizon, this diagonal black line, represents the orbit of a massless particle going radially outward at the speed of light. And that is actually going radially outward on a null geodesic, or light-like geodesic. So through every point on the horizon, as I said last time, there's a light-like geodesic, which for a spherically symmetric black hole is just the orbit of going outward, going the speed of light outward in the radial direction. So we parameterize the geodesics by v, and I write x for angular coordinates on the horizon. And since the v direction is null, the horizon metric in general, this should be equal sign, not a plus sign. The metric is that ds squared is something times dxa dxb plus 0 times anything with the dv in it, because the v direction is null. Now, for the generalized second law, the interesting case is that in the classical limit, the area is constant, because if it's not constant, it's increasing. And if it's increasing, then the classical increase in the area term overwhelms whatever's happening to the quantum entropy. So we want to look at a black hole that classically has a constant area. Now, we used Einstein's equations to prove that if the area is constant, that means the metric is stationary. That means independent of v. I won't repeat the proof, but I just remind you that we use Einstein's equations to prove that. And at the same time, we also explain the proof of the Hawking area theorem, that if the area isn't constant, then it's increasing. Now, as I remarked, on such a stationary horizon, the quantum fields have a preferred state, which is important. There are a few things I should have told you about it. One is that if the black hole is a standard Schwarzschild black hole that existed for all time, the state I'm talking about is just the Hartle-Hawking state, restricted to the region we're interested in. So the Hartle-Hawking state would exist throughout all of the analytically continued black hole space-time, most of which we don't have. But we do have this portion of it, the portion of it in white in this picture. And we can just take the Hartle-Hawking state of the quantum fields restricted to this region. So that's one way to describe the state that we're talking about. Here's another way. As Aaron Wall explained, if we make a lattice regularization of the angular coordinates with a discrete set of values that I'll call x sub lambda, then the Hilbert space of the regularized theory is just a tensor product. H is the tensor product over all values of lambda of h sub lambda. For each lambda, the angles are fixed to a point, but we still have the v direction, which is one dimension. And there also, although I've suppressed it, is the orthogonal u direction. So at each value of lambda, we'd have a two-dimensional space-time living at that particular value of x. And if we let omega lambda be the ground state in the Hilbert space h lambda of the regularized theory, and we let omega be the tensor product over all lambda of omega lambda, then that's the state we're talking about. It's also the same as the Hartle-Hawking state restricted to the horizon. Now let sigma f be the density matrix of this state restricted to the future of some cut at v equals f of x. Then, you see, in the first lecture, we analyzed two-dimensional Minkowski space and a quantum state on a null line in two-dimensional Minkowski space. If you make a lattice regularization and just look at what happens at a particular value of the angles, we're back in 2 dimensions. And so we deduce this formula, well, except for the sum over lambda, we deduced this formula in the first lecture. When I take if I don't take the logarithm, the density matrix would be a tensor product of rho lambda. But when I take the logarithm, we get a sum over lambda of what we did in the first lecture. In the continuum limit, the sum becomes an integral, and we get the formula that I used yesterday for minus the logarithm of the density matrix of this special state restricted to the future of the cut. So on this page, I tried to give another explanation of what was the state and why it satisfies that condition. Now, the next thing we did last time was to use the density matrix, to use the Einstein equations to compute the quantum correction to A sub f. A sub f is the horizon area at a cut v equals f of x. And using the Einstein equations, we got a formula that A sub f was minus 8 pi g times the matrix element in whatever state psi we're studying of this funny operator. But for reasons that I explained yesterday, but I tried to give another explanation here, this funny operator is minus the logarithm of the density matrix in that particular state related to the Hartle-Hawking state. And the expectation value in the state psi of log sigma f is the same as the trace of rho f times log sigma f. In other words, log sigma f is an operator that only acts to the future of the cut. So we can replace the state psi by its density matrix to the future of the cut. So the quantum correction to the area term in the generalized entropy then turns into this trace. And the entropy term, to begin with, is the von Neumann entropy minus trace rho log rho. So therefore, the order h bar contribution to the generalized entropy, it's a sum of 2 terms. One is minus trace rho log rho, and the other we just evaluated to be trace rho log sigma, where the 4g cancels out. And this is the definition of the relative entropy with a minus sign. So what we learned by that calculation is that the order h bar correction to the generalized entropy is simply the relative entropy between the state we're interested in and the, if you like, the Hartle-Hawking state to the future of the cut. So now we want to compare 2 cuts. So like yesterday, I'm now drawing a different picture. Instead of always making it look like, well, this picture makes it look like the black hole horizon is blowing out to infinity at the speed of light. But actually it has a fixed size and is time independent. So here's a different picture of the same thing, where V runs vertically. And I'm trying to emphasize that the black hole horizon is really stationary in the classical limit. Stationary means time independent. So now we make a cut F, we have another cut G, which is to its future. And monotonicity of relative entropy says that the relative entropy on the first cut is bigger than on the second. But since the relative entropy is minus the quantum correction to the generalized entropy, we get the same inequality for the generalized entropy, but in the opposite direction. So monotonicity of relative entropy becomes the generalized second law, that the generalized entropy in the smaller region V, but here, instead of saying smaller region, you should think later cut. The generalized entropy at a later time is bigger than it is at the earlier time. So that's the generalized second law. And as I tried to explain also yesterday, the fact that there is a generalized second law that the entropy increases is because Bekenstein's horizon area was a thermodynamic entropy. It's a coarse-grained entropy where you average over everything that's behind the black hole horizon that you can't see and replace it by just the horizon area, which in some sense, is measuring your ignorance. And your ignorance can increase as more matter falls behind the horizon. And that's why the generalized entropy is not constant. In general, it increases. So by now, we've spent the better part of 2 lectures, plus a little bit of bonus time today, discussing the Beckenstein-Hawking formula, entropy equals horizon area. As was clear from the beginning, this is a kind of thermodynamic entropy, which increases. It reflects coarse graining over the black hole interior. It's appropriate if you're only making observations outside the black hole. And that's why there's a generalized second law. We found that to understand more deeply the generalized second law and the Beckenstein-Hawking entropy, we had to consider the entropy of the quantum fields outside the horizon to be the microscopic or fine-grained von Neumann entropy. Now, this question might motivate you to ask, is there a geometrical formula for some sort of fine-grained version of the Beckenstein-Hawking entropy itself? We're asking this question with hindsight. The answer was found, I would say, not quite by asking that question, in a somewhat different way. But there is an answer. It was found by Ryu and Takanagi, with later improvements by several others, and I'll mention a couple of the improvements. And note that the Ryu-Takanagi work actually preceded the things I've primarily told you about. Cassini and the Bekenstein bound and Wall and the generalized second law were a couple of years after Ryu and Takanagi. But they were after Ryu and Takanagi, but before Ryu and Takanagi was sort of put in this framework that I'll try to put it in the rest of the lecture. Now, to motivate the formula, we can consider a maximally analytically continued black hole solution describing an entangled state of 2 universes. So I've drawn the Penrose diagram for the anti-de Sitter version, but I was tempted to illustrate the same idea using the Minkowski space version. Now, I know you're probably not all familiar with this picture, although probably many of you are. So I'll try to explain it briefly. If you take the Schwarzschild solution, well, let's go back to the black hole we've studied. Here we imagine that there's a star, but outside the star is empty space. And we have a vacuum solution of the Einstein equations in this white region. That solution is called the Schwarzschild solution. It's the unique spherically symmetric solution. You could ask, what would happen if there wasn't a star? Well, if there wasn't a star, you'd continue the Schwarzschild solution inward, and you could continue it as far as it goes. And what happens wasn't really understood for more than 40 years after Schwarzschild. But what happens is quite amazing. The analytic extension of the Schwarzschild solution describes 2 universes, not 1. This is one asymptotic world with this vertical line being at spatial infinity. And here's another such asymptotic world. In between them is a black hole with a singularity in the future, and what's called a white hole with a singularity in the past. So to an observer living on the right, this line here is the future horizon. This observer cannot see behind that horizon. And to an observer on the left, this line is the horizon. This observer can't see past that horizon. So this is this is the pure form of the black hole solution of general relativity with no matter. It rather amazingly describes 2 universes that are joined geometrically in this fashion. So if you cut it on a surface at constant time, the metric blows up over here. This is spatial infinity here. Then the size shrinks. You pass through a wormhole, and going out through the wormhole, you come out into a second universe. But you cannot travel from one universe to the other because you can't travel at more than a pi/2 angle to the vertical, which would mean parallel to the horizon. If you start over on the left and you go to the right at a pi/2 angle, that means radially at the speed of light, you'll go parallel to the horizon and you'll end up at the future singularity. You'll never reach the right side. So that's a lightning introduction to that solution. But unfortunately, if you haven't seen it before, it's going to be hard to really appreciate based on that kind of explanation. Now, Gibbons and Hawking in the 70s explained that this picture represents two entangled worlds in the thermofield double state. That means an observer on the right sees a black hole, an observer on the left sees a black hole. Each black hole is in all possible states, but whatever state I, the first one, is in, the second one is in the same state, with a probability which is the exponential of minus the energy of that state times beta, 1 over the Hawking temperature, except I think I dropped a factor of 2 in this formula. It should be beta over 2. So anyway, this geometry is related to this thermofield double state. And if you construct from the thermofield double state a density matrix for just the right universe or just the left universe, you'll get a standard thermal density matrix. That's actually why it's called, this time I did, here on this page, I did write it in the 1/2. The 1/2 is important in getting this answer. When you take a partial trace over the left or right space, you'll get a standard thermal density matrix for the one you don't trace over. Now, according to Gibbons and Hawking, as adapted to antidissident space, the entropy of this density matrix is the horizon area. And for this ideal solution, it does not matter which horizon one picks or where one measures it. So you could make a cut of this horizon anywhere, and its area is a constant. And you'd have precisely the same area if you made a cut in the far past. It would be there the Whitehall horizon. You could likewise make a cut of the other horizon. Either horizon has precisely the same area no matter where you cut it. And I believe this fact may have, in the 1970s, kept people from asking a question that, from a modern point of view, you want to ask. So horizon, so in the Bekenstein-Hawking relationship of area to entropy, the area, first of all, is the area of the black hole horizon at any time you want to look at it. And the entropy is the thermodynamic entropy at that time. But there's something else we could try to do. We could try to ask if there's a version of the Bekenstein-Hawking entropy or an analog of the Bekenstein-Hawking entropy, which would give us the fine-grained von Neumann entropy. Now, to make this into a real question, we need to go to a situation where there are differences. And in this idealized model, because each horizon has the same area no matter where you cut it, people considering that idealized model weren't motivated to make the definition I'm going to give you in a few minutes. But from a modern point of view, we may ask the following question. Consider two observers, one living on the left and one on the right, who decide to disturb this system. Well, there's a lot you can do. From a quantum mechanical point of view, you can apply a unitary operator to the Hilbert space on the left. The left observer can do that. The right observer can apply a unitary operator to the Hilbert space on the right. But in terms of gravity, what you can do is even more obvious. You could throw tables and chairs into the black hole, or anything else you want to. So here I imagine that the right observer is tossing something into the black hole. I hope it shows up that it's meant to be in blue, not the black lines I had before. So the right observer has disturbed the system by throwing in something. It could have been elementary particles, it could have been tables and chairs. Of course, it causes the horizon area to increase. So now the horizon area, if you measure it here, will be bigger than it was here. And over here, it will be bigger than it was here. But the problem is time symmetric. So the right observer can also create a state that had additional particles in the past. That's less obvious intuitively, but it's kind of obvious from the quantum mechanical point of view. From the quantum mechanical point of view, the most general thing you can do is act with a unitary operator. It's completely time symmetric. So you can disturb, if you can disturb the future, you can also disturb the past. So a general manipulation by the observer on the right will involve throwing in particles that go into the future, but creating a different state of the system where there are particles that emerge from the past. And you'll see that the right observer can affect what's in this triangle, and this triangle, but can't do anything that affects this fourth triangle, which is not in causal communication with the right observer. The right observer can only send things in that go at an angle at most pi/2 to the vertical. So they can reach 3/4 of the picture, but not the last quarter. Now, if you do this, when you make this disturbance, you cause the right moving horizon area to increase as it goes along. And if you make a disturbance in the past, you make the left moving horizon area increase as it goes along into the future. So in this picture, this right moving horizon area increased as it went into the future, and this left moving one also increased as it went into the future. Now the left mover can do this, the observer on the left side can do the same. So I've drawn in red particles that the left observer created that go into the future or maybe go into the past. And by now the picture is quite a mess. And you can see there's no place in this picture that the horizon area is guaranteed to be constant. Because whenever the horizon crosses one of these ingoing or outgoing red or blue lines, its area will increase. It'll always increase because of the Hawking area theorem. So Bekenstein and Hawking will tell you that if you measure the horizon area at some time, whatever its area is at that time, you should think of that as the thermodynamic entropy of the black hole, or at least the part that captures what's behind the horizon. And then if you want to generalize second law, you should also include the entropy outside the horizon at the same time. That means on a cut from the same moments. Now, I've described that in terms of geometry, that the left and right observers throw particles into the future or the past from either the left or the right. And these particles can reach almost anywhere in the picture. There's precisely one point they can't reach in that picture, which we'll get to in a moment. All these manipulations change the state. So let's look at it from a quantum mechanical point of view. Whatever the left and right observers do can be described as acting with a unitary operator. The left observer can act with a unitary operator UL that only acts on the left Hilbert space HL, and the right observer can act with a unitary operator UR that only acts on the right Hilbert space HR. The two observers can do a lot to the system, but they can't do everything. They can only change the left or right density matrices by conjugation. Because when you act on the state with this unitary, you'll find if you construct a density matrix for the left system by tracing out the right system, that UR does not matter, and UL only transforms the density matrix by conjugation. Similarly, the right density matrix only transforms by conjugation. And this conjugation does not change the entanglement entropy between the left and right. I should have emphasized before we started, the state was pure, but the reduced density matrix for left or right was thermal. So its entropy was the thermodynamic entropy of what was a thermal entropy, an entropy of a thermal system. But since the state was actually pure, that was a thermal system whose entropy is also the entanglement entropy in this pure state. So before the left and right observers did anything, the entanglement entropy, the entropy of left and right density matrices was the entanglement entropy of this pure state. After they do their will, acting with UL tensor UR, they have a different pure state, but the entanglement entropy is the same. So whatever they've done will not change the entanglement or fine-grained entropy. So the left and right observers can do whatever they want, but they can't change the entanglement entropy between the two sides. Now, let's ask whether the entanglement entropy between the two sides can be interpreted in terms of geometry in the spirit of Bekenstein and Hawking. Well, if it can be represented by something in geometry, it'll be something that observers on the two sides cannot change. Ryu and Takiyanagi identified such a quantity, not by following the logic I'm telling you. Well, okay. Ryu and Takiyanagi, as interpreted by later authors, identified such a quantity. Namely, I left out a factor of 4. It should be A over 4G H bar, where A is the area at the one point that the left and right observers can't do anything to. You see, they can send in signals from the left and right boundary that travel no faster than light into either the future or the past. And those signals can reach everywhere in this picture except one point where the two horizons cross. So the only reasonable geometric candidate for what kind of area should be the entanglement entropy, which the observers can't change, or in other words, the fine-grained, microscopically defined entropy, the only reasonable candidate is that the area we have to use is at this bifurcation point, which the two observers can't change. It's the only area in the picture that they can't change. So it's the only area in the picture that's a conceivable candidate for representing the fine-grained or entanglement entropy between the two sides. So in this example, the key point is the bifurcation surface where the two horizons cross. The observers on left and right can do nothing to change it. But there's another characterization of that point, which is more useful for generalizations. The area at this point, okay, every point on this picture represents a two-dimensional surface if we're in 4 dimensions. Because remember, in a Penrose diagram, we've suppressed the angles, and we're only showing time which runs vertically, and the radial distance runs horizontally. So every point represents a two-dimensional surface, but the area of the surface is stationary. Well, okay, it's a function on the picture, but that function is stationary of the bifurcation point. That's what, you see, before the left and right observers started to change the state, the horizon area was completely constant on both diagonal black lines. And what's left from that is that the area at the point where the lines crossed is unchanged, and moreover, its first derivative is still 0. So the formulation of Ryu and Takiyanagi is that, as slightly elaborated by others, is that the entanglement entropy is the area over 4G H bar of an extremal surface. That's, okay, I'll say it better on the next slide. But anyway, in the generalization, what's important is that this bifurcation point represents a surface whose area is extremal. That means if you move the surface in any direction, to first order, its area does not change. So, as I said, that's left over from the fact that before the blue and red lines were sent in, the area was completely constant along both black lines. Now, since the picture has become rather busy, let's go back to where it was before the left and right observers started manipulating the system. Well, okay, I've already told you this, but the only place in the picture where the left and right-hand observers can't change the geometry is the bifurcation surface where the two horizons cross. So if fine-grained entropy is going to be something in the geometry of the picture, it should be the area of the surface if it's any kind of area. Now, Ryu and Takiyanagi did not originally formulate their idea primarily for the case of a pair of entangled universes. They considered a single asymptotically ADS spacetime. So ADS means antidissident space, which means negative cosmological constant. For mathematicians, it means hyperbolic space, negative curvature. And so it's a complete Riemannian manifold with a conformal boundary that's infinitely far away. But it's convenient to draw conformal pictures where, like in the Poincare bowl model or Poincare sphere model, Poincare disk, the infinity is projected to a finite distance so that you can see it better. So they considered a single asymptotically antidissident spacetime, which they moreover assumed to be time independent, which made the right definition more obvious. So, okay, what I've drawn you could think of as the Poincare disk. So it represents hyperbolic space, if you like. We're really in a hyperbolic space-time, but they've assumed it to be time independent. So we take a cut at time 0. So we have hyperbolic space, which we represent by the disk. The boundary of the disk is infinitely far away, but we've projected it to finite points. And then a geodesic in this space, what is actually a geodesic in the hyperbolic space, is a curved line in this model. So L is meant to be a geodesic. That's a curve of extremal area in a 2-dimensional picture. And then Ryu and Takinagi imagine dividing the boundary into 2 disjoint regions, in this case C and D. And they consider the reduced density matrices rho C and rho D of the vacuum state psi, or any time independent state, but it could be just the vacuum state, in regions C and D. So even though the state is pure, if you consider only measurements on C or only measurements on D, there will be a von Neumann entropy, an entanglement entropy, and they'll be equal because the state is pure. And they propose that the entanglement entropy of the reduced density matrix is the area of a minimal area surface, L, that separates the 2 boundary regions. So if space-time is 3-dimensional, and therefore space is 2-dimensional, as I've drawn, then the minimal area surface L is a geodesic. So that's a perfectly good example of this. If you take at face value the 2-dimensional picture, then L is a geodesic in the hyperbolic space. And its area is its length. Well, it's usually called area in this context, but if it's actually a geodesic, you might prefer to call it length rather than area. But anyway, its length or area, or in higher dimensions volume, is supposed to be the entanglement entropy. Now this is a bit tricky because actually the length of this geodesic is infinite because the boundary is infinitely far away. But remember that entanglement entropy is also ultraviolet divergent in quantum field theory. And here, these entropies are defined in the boundary quantum field theory, which is an ordinary theory without gravity. So these entanglement entropies are, in fact, ultraviolet divergent. And part of the story of Ryu and Takinagi is that the divergence of the length matches the divergence of the entanglement entropy. And the claim is that the divergences match, and cutoff versions of the entropies match cutoff versions of the areas or lengths. Now, so this was the original formulation of Ryu and Takinagi, and it took a number of further steps before it was natural to think in the way that I used in motivating it. So in motivating it, I considered this picture with arbitrary perturbations, and then asked what is there that in the entanglement between the 2 sides that the 2 observers can't manipulate. I use that to motivate the work of Ryu and Takinagi, but that involves some hindsight. What their actual original proposal was what I've sketched here. Now, soon after they made this proposal, it was understood that the Ryu-Takinagi formula converts rather subtle statements of quantum information theory into simple facts of geometry. And I'm going to give 2 of the basic examples. Consider a bipartite quantum system AB with Hilbert space HA tensor HB, which I'll call HAB, and density matrix rho AB. We can also define the reduced density matrices rho A and rho B that we get by taking partial traces over B or over A. Well, we can define the entropy SAB, as we did yesterday, or even maybe in the first lecture, minus the trace over AB of rho AB log rho AB. And similarly, we defined SA and SB. And the important property called subadditivity of entropy says that SA plus SB is equal to or bigger than SAB. This actually follows from positivity of relative entropy. We consider rho A tensor rho B as a second density matrix on HAB. So on HAB, we have 2 density matrices. One is rho AB and one is rho A tensor rho B. If you make measurements only on A or only on B, you'll get these two density matrices are equivalent. But if you look for correlations between A and B, if you make simultaneous measurements of both A and B, then rho AB describes correlations which are absent in rho A tensor rho B. So what rho A tensor rho B is it's equivalent to rho AB if you only care about one system or the other, but if you care about the correlations between the two systems, you lose them when you go to rho A tensor rho B. Now, as I sketched the proof in the first lecture, relative entropy is non-negative. So in particular, relative entropy between these two density matrices is non-negative. And it's defined by this formula. But since the logarithm of rho A tensor rho B can be written in terms of log rho A and log rho B, if you plug that into this expression and calculate some of the partial traces, you'll learn, well, I've written here what you have to do. You have to observe that if nothing depends on B, if the operator you're interested in is the identity on B, you can take the partial trace over B and replace rho AB with rho A. So you have this nice fact, and this you recognize as minus SA, minus the entropy of system A. Of course, the same is true with A replaced by B. If you do that in this formula, then the right-hand side becomes SA plus SB minus SAB, and therefore the inequality of positivity of relative entropy is that SA plus SB minus SAB is non-negative, which is called subadditivity. So that wasn't too hard. As a calculus exercise, it was slightly non-trivial, but not too difficult. Now let's give the proof based on geometry. Of course, this was a universal proof for all density matrices. The proof based on geometry is only for density matrices that have a holographic interpretation. But let's see how it works when the Ryu-Takanagi formula applies. So, well, I didn't shade it now, but this is the same point gray disk as before. And now A and B are two portions of the boundary. And the density, the entropy of the system AB, you take the union of AB, you take a minimal area surface in the bulk that's homologous to AB. That's just a geodesic between the two endpoints. So it bends like this into the bulk. Well, it bends in the point gray disk model, but in reality, in hyperbolic space, it's simply a straight line, a geodesic. The entropy of A, on the other hand, is similarly the length of a geodesic between these two endpoints. And for SB, you have the length of a geodesic between these two endpoints. And the inequality says that the length of this straight line between 2 points is less than the length of the line between the same 2 points that's not a geodesic, because it bends over here. So in other words, subadditivity of entropy became the triangle inequality for lengths. So that's satisfying in the sense that that's a non-trivial test of the RT formula. If the RT formula is going to be correct, it has to satisfy all general properties of entropy, and this is one. And the triangle inequality shows it's satisfied. Much more subtle is what's called strong subadditivity of entropy. This is a rather deep theorem. Here we consider three systems ABC with the density matrix rho ABC on the tensor product of three Hilbert spaces. By partial traces, we reduce density matrices. We define reduced density matrices, such as rho BC, which is the trace over A of rho ABC, as well as others. Then then you see on ABC, we could consider the density matrix rho A tensored rho BC. And likewise on AB, we could consider as before rho A tensor rho B. And since system AB is smaller than system ABC, in other words, we're forgetting some degrees of freedom, the monotonicity of relative entropy, which was proved by Lieb and Oskal in the same paper, says that one relative entropy is bigger than the other. Now, by a similar computation to the one on the last slide, and if you're interested in this material, you should do that computation yourself, you can show that this inequality is equivalent to strong subadditivity. So in contrast to additivity, which has a simple proof that I gave here, strong subadditivity is a rather difficult theorem. But it has an easy proof in holography. Here's the proof for states with a holographic interpretation using the RT formula. So here are three regions, A, B, and C. So S, A, B, C, I've assumed that they're end-to-end. So I've assumed A and B share an endpoint and B and C share an endpoint. We don't have to assume that, but it's an interesting case for the formula. So then ABC is a region with these two endpoints, and its entropy, according to Ryu and Takanagi, comes from this geodesic that I've labeled SABC. The entropy of B is associated to this geodesic, and the entropy of AB comes from this one, and BC comes from this one. So strong subadditivity of entropy says that SAB plus SBC, these two geodesics, are longer than this one plus this one. All the lengths are actually divergent, so the proper statement involves cutting off lengths near the boundary. But you see, the reason the statement is true is that SABC is less than going here and here, which is a non-geodesic path from A to C. And SB is less than going from here to here. So in the context of holography, the rather deep theorem of strong subadditivity comes down to two applications of the triangle inequality. So several important improvements of the RT formula were made by later authors. So Ubani, Rangamani, and Takanagi extended the RT formula to a possibly time-dependent case. So Ryu and Takanagi had assumed time independence, and therefore they had worked at a slice at fixed time, and all their discussion was in a spatial manifold at fixed time. And in a spatial manifold, it makes sense to minimize length or area. So their proposal involved minimizing the area or length at time zero of a surface that's homologous to the given boundary region. So L is homologous to C, for example, through this homology, and L is also homologous to D. But minimizing areas or lengths only makes sense in space, not in space-time. In the time-dependent case, there's no such thing as a minimal surface, because if you let a surface wiggle in the time direction, that will always reduce its area. So you have to stop talking about minimal surfaces and instead discuss extremal ones, which was actually the case in the example I gave in motivating the RT formula. So the intersection point of the two diagonal black lines is a surface of extremal area in space-time. So that's a rotationally invariant surface in a rotationally invariant picture. But even if you let it wiggle in a way that goes away from rotational symmetry, its area is stationary. Well, it's not minimal though, because wiggling it in the time direction will reduce its area. So in the time-dependent generalization of the RT formula, it's extremely important to discuss extremal surfaces, not minimal ones. So actually, the motivating example I gave for the RT formula was really an example of the HRT refinement of the RT formula. So that was one important refinement of the RT formula. Now, and I'll get to another in a moment. Now, when space-time is time-dependent, the simple geometric proof of strong subadditivity of entropy doesn't work. And that's because all the entropies are, well, in 2 + 1 dimensions, they would be represented by geodesics. But the geodesics would not be in a common 2-dimensional space-like surface. The geodesics are geodesics in a time-dependent space-time. They might go forwards and backwards in time relative to each other. One might be to the future of the other. They don't, well, so in this picture, for example, SAB and SBC correspond to geodesics that intersect. In a time-dependent situation, they're still one-dimensional, but now they live in 3 dimensions. They generically won't intersect. There's no space-like surface that combines them both. And you can't prove strong subadditivity just from the triangle inequality. But Wall showed that by using properties of Einstein's equations, you can map the various extremal surfaces to a common Cauchy hypersurface and prove strong subadditivity. The properties of Einstein's equations you have to use are similar to the ones we used yesterday. You have to use the Einstein-Ricciardori-Sachs equation, constraint equation for a null hypersurface. And just as Einstein's equations fit beautifully into exactly what we needed for the generalized second law, they fit equally beautifully in what we need to prove strong subadditivity in the time-dependent case. I wish I could have explained it, but it would have made another lecture, or at least another half lecture. So that's what I'll say about the HRT generalization of RT. But there was another important refinement. Well, first of all, Lefkowitz and Modesena gave a path integral proof of the RT formula. Their proof was similar to the Gibbons-Hawking Euclidean analysis of black hole entropy from the 70s. Unfortunately, I didn't have time for the Gibbons-Hawking analysis, and therefore we don't have the foundation to explain the Lefkowitz-Modesena arguments. But it's a relatively simple argument if you're familiar with if we'd had time to go into more detail on what was done in the 70s, it would be a simple extension. But Faulkner, Lefkowitz, and Modesena shortly afterwards made the following important observation. Well, the RT formula that the entropy is, I wrote minimal, but this should be extremal, that the entropy is the extremal area over 4gh bar is a classical approximation. And the quantum generalization is just to include the entropy of the quantum fields in what's called the entanglement wedge between the minimal surface and the boundary. So for example, to compute the entropy of region C in the boundary, we should include the bulk entropy in the orange region. So the region between the entanglement surface, the RT or HRT surface. So let's actually discuss the time independent case so we can simply draw simple pictures in space and forget about time. So in a time independent case, we take a slice at a given time. So if we're in 2+1 dimensions, we draw the Poincare disk, hyperbolic 2 space. We have a portion of its boundary, a geodesic connecting the two ends in the bulk. And then the orange region is the region bounded by that geodesic and C. That's called the entanglement wedge. Well, it's really called a wedge because of the space-time picture. So if you extend this, what's really called the entanglement wedge is the domain of dependence of the orange region in space-time. But I think for what I'll tell you, we will just draw pictures at constant time. So I'll just draw this orange region. So what Lefkowitz and Modesena explained is that the quantum correction to the RT formula turns it into what you could call the generalized entropy of the minimal surface or minimal geodesic L. So the von Neumann entropy of the density matrix in region C. So C is a region in the boundary. So what I call rho C is the density matrix of the boundary theory reduced to the region C. And it has a von Neumann entropy. And the RT formula for its von Neumann entropy was just the area of L over 4gh bar. But Lefkowitz and Modesena corrected that and say you have to add S out, where S out is the entropy in the orange region. And by now we know that that means the von Neumann entropy of the bulk quantum fields in the orange region. So in other words, fine-grained entropy is given by the same generalized entropy that Bekenstein started with, but for a different surface, an extremal surface rather than the horizon. So after, well, okay, this term was added 7 years after Ryu and Takinagi, and it still took a little bit before it was fully appreciated. But the bottom line is that what Ryu and Takeyanagi told us is that if you want to do fine-grained entropy rather than thermodynamic entropy, then instead of an arbitrary cut of the horizon, you should take an extremal surface in space-time and otherwise use Bekenstein's definition as refined by Sorkin and others who learned that S out is the von Neumann entropy. So I made that too complicated. But to go from Bekenstein-Hawking thermodynamic entropy to fine-grained von Neumann entropy, you just replace a cut of the horizon by an extremal surface, and otherwise you do the same thing. That's the bottom line from various refinements of the RT formula. Now we're going to have some fun, or at least I hope if you're with me, it will be fun for the rest of the talk. And we're going to, we'll start by asking the following. Consider a holographic observer who has complete access to the region C of the boundary with density matrix rho sub C. What part of the bulk can this observer describe using only the information contained in rho sub C? Well, I'm only going to give a heuristic answer, which to me is actually more convincing than the technical answers that you can find in the papers. Suppose there's a qubit. A qubit just means a particle, like a spin-half particle, that can have some entropy. Suppose there's something in the orange region. If there's something in the orange region, it contributes to the entropy of rho sub C. But if there's something that's in the gray region, it does not contribute to the entropy of rho sub C. Well, the most reasonable interpretation of this is that rho C describes the orange region, but doesn't describe the gray region. And this is now understood as the appropriate interpretation of the form. Well, let me see. So adding what might have seemed like a small quantum correction, what in many situations would be a tiny quantum correction to this big classical formula might not seem like such a giant step. But it suggests this statement, which also at first, it's not so obvious why it's important, but proves to have fantastic consequences, most of which I really can't tell you about today. I'm only going to be able to tell you one or two things. But the conclusion is, from this generalized entropy formula, that generalized entropy formula suggested that rho sub C, the density matrix of the boundary region C, is describing what's in the orange region and not what's in the gray region. And that's what's understood today to be the correct interpretation. So it leads to the idea of entanglement wedge reconstruction. The boundary density matrix rho C describes the bulk physics in and only in the orange region. That's the starting point for a lot of the contemporary research. Now, all I'm really going to do with it is to explain an apparent paradox, or what might look like a paradox, and then I'll tell you how to resolve the paradox. But I wrote 1995, which is surely wrong. Maybe these papers were in 2015, but they're certainly not in 1995. So we're going to consider a time-independent situation, and we'll divide the boundary in 3 more or less equal parts, and there'll be some unknown particles in the red region in the center. So again, to make easy pictures to draw, I'm assuming we're in 2+1 dimensions. So at time 0, we've got the Poincare disk, and I've divided its boundary into 3 regions, A, B, and C. And then I've connected the endpoints of those 3 regions by geodesics, which in this picture look like curved lines, but they really are geodesics in hyperbolic space. And then I've drawn in red a region in the center that has some unknown particles that we'd like to know about. And the question is, can a boundary observer know what's in the red region? Well, a boundary observer with access only to region A or only B or only C has no information about the particles in the central region. But if you have access to 2 of the regions, say A and B, you can reconstruct what's in the central region. Because if you take A union B, that's the region that goes all the way around here in the boundary. The geodesic that bounds it is this one. And the region that's between that geodesic and the union of A and B is the region I've now drawn in orange, and it includes the red region. So a boundary observer with access to two of the regions can learn what's in the red region, and a boundary observer with access to only one of them cannot. This may sound paradoxical at first. Can information about a quantum state, in this case whatever is inside the orange region, really be shared between three observers in such a way that any one of them knows nothing, but any two of them together know everything? Well, here's where the answer is yes, it is possible. And the fact that it's possible is one of the main ideas in quantum computing. There won't be time to explain that. So instead, I'm only going to entertain you, at least I hope it will be entertaining if we're not all too tired, by explaining how to do it in the classical limit. And then I'll just very schematically say a word about the quantum case. Let's practice with the classical situation. As a preliminary, can you send a secret message to two friends A and B in such a way that either of them learn nothing, but if the two get together, they can learn the message? How would you do that? Well, here's one way to do it. First, you write your message as a binary number X. We can assume all your friends know how you encode English or Korean messages as binary numbers. So there's no secret there. There's no secret in how you encode it, but the actual number is the secret. So whatever you wanted to send, you turn it into a binary number. Now you pick a random binary number Y with the same number of digits, the key. You send Y to A and you send X plus Y to B. You see, both A and B have received random numbers and learn nothing. But if A and B get together, they can compute X plus Y minus Y equals X, and they learn the message. So you've sent the message in a distributed way to your two friends. If they cooperate, they learn the message. If they are unable to cooperate, they learn nothing. Now suppose you have three friends, A, B, and C. You want to send a message in such a way that any one friend learns nothing, but any two of them cooperating can learn the message. Well, again, you encode the message as a binary number X, and you pick three random numbers, Y1, Y2, Y3, with the same number of binary digits as X. You send your friends the following. A receives Y1 and X plus Y2. B receives Y2 and X plus Y3. And C receives Y3 and X plus Y1. So each one individually has received two random numbers. But you should be able to see that although any one friend learns nothing, any two, if they get together, can reconstruct the secret message. Because, for example, if A and B get together, they have both Y2 and X plus Y2. And then by subtraction, they find X. And similarly for any other two pairs. Now, in this procedure, there was a key step that doesn't have a quantum analog. You had to make multiple uses of the message X to compute the numbers X plus Y2, X plus Y3, and X plus Y1 that you sent to your various friends. For example, you might have entered the same number into an adding machine 3 times. Anyway, whatever you did, it can't really be imitated quantum mechanically. But nevertheless, there is a quantum procedure that does the job. So I'm just going to give a very schematic statement without any attempt at a proof. You have an unknown quantum state psi. Well, first of all, what it means in quantum mechanics to send a secret is that you send the quantum state psi, which you may not know. It might be an atom in some quantum state. You don't want to measure it, because if you measure it, you disturb it. You could measure the spin in the z direction, but maybe your friend wants to measure the spin in the x direction. And if you measure the spin in the z direction, you'd spoil your friend's ability to make the measurement that he or she might choose. So what you want to do is to send this unknown quantum state without disturbing it to a friend who in turn could make a measurement of his or her choice. So in my motivating example, psi is the state of the system inside the red region. And the entanglement wedge reconstruction predicted that holographic duality has the property that any two boundary observers working together can determine what's in the red region, but one alone cannot. So the holographic duality is playing the role that you played here, where you encrypted the message in all these random numbers and set them to the three friends. So the three friends that correspond to regions A, B, and C. The message is whatever's inside the red region. And the one who's doing the encoding is gravity and anti-de Sitter space. And the code by which the message is transmitted to the boundary is just the bulk boundary duality of anti-de Sitter space. So, okay, but how do people who want to build a quantum computer imagine doing something like this? So they encode psi in a tensor product, HA tensor, HB tensor, HC, of three Hilbert spaces in such a way that with access to only one of them, you learn nothing about psi, but with access to two of them, you can reconstruct psi. In fact, if HA, HB, and HC all have the same or similar dimensions, and H is smaller, a fairly generic embedding of H into the tensor product of the three will do the job. For generic embedding iota, no matter what state psi and H we start with, the reduced density matrix of I of psi for any one of the three Hilbert spaces is a multiple of the identity and contains no information. But the reduced density matrix on the tensor product of two of them contains the information needed to reconstruct psi. So unpacking this and convincing you it's true would sort of be a longish story. But well, what the statement means is that given rho AB, the reduced density matrix on two factors, you can describe the outcomes of arbitrary experiments performed on psi. But I won't really, I won't try to prove the assertions made on this slide. I'm only going to say that there's standard assertions in quantum computer science. And in fact, such redundant encoding of quantum information is believed to be necessary in the functioning of any future general purpose quantum computer. The reason is that the components will be noisy. And to fight the noise, you need to encode information in a redundant fashion. So here, you see, the bulk state, or in particular, the part of the bulk state in the red region, is encoded in the tensor product of the three Hilbert spaces on the boundary, but it's encoded in a redundant way such that if one of the three got lost, with the other two, you could reconstruct the bulk state. That's what we predict from entanglement wedge reconstruction. So this story where just two of them, the entanglement wedge includes the red region, and you could forget region C, is telling us that the bulk to boundary dictionary of anti-de Sitter space is solving this problem of quantum computer science with the redundant encoding, which they do roughly this way, but that was a very schematic description, that's believed to be necessary to overcome the noisiness of the components of a future quantum computer. It can be shown that with the help of redundant encoding, it's possible in principle to get reliable results from a quantum computer that's built from noisy components. The noisy components can't be too noisy. They have to usually work. But if your components all work 95% of the time or whatever, then with suitable redundant encoding, you can fight the errors and get reliable results, even though you're doing a long calculation during which many individual components are failing. So to the computer scientists, the importance of this redundant encoding is that it enables you to get a correct result from a computation, even though many components fail while you're doing the computation. Now, I'm going to resist the temptation to say more. I think I've probably imposed on your patience quite a bit during what's ended up being more than 3 hours, probably. I'll just conclude that by saying that I hope in these lectures, I've given you a taste of the uncanny way that Einstein gravity intertwines with quantum mechanics. I haven't brought the story up to date, which seemed impossible in just 3 lectures, but I think I've brought you to within hailing distance of the most recent papers, by at least introducing the idea of entanglement wedge reconstruction. I resisted the temptation to try to list the topics I haven't explained because I couldn't see a sensible way to do so concisely. And so I'll have to stop here, hoping you've enjoyed the lectures and that some of you at least will become interested in some of the even more recent developments. Thank you.
Right. Thank you very much. Questions, comments? There was a early question that's waiting, but I mean, before we while people warm up for questions, can I ask you something? I mean, I was a little bit confused about the bifurcation surface as the extremal surface. So
Yes.
if I imagine actual black hole made from collapse, that bifurcation surface doesn't exist as part of space-time.
That's correct.
But am I still supposed to use this eternal, I mean,
Well,
I guess.
Well, let's discuss about. Okay, you're supposed to look for an extremal surface in that space-time.
In that space-time, actual space-time.
Yeah, but it's allowed to be empty. So let me just answer your question for the simplest case. Suppose a black hole formed from collapse from a pure state. And suppose you only ask very simple questions about it. There's actually a new paper by Engelhardt, Wall, and I'm forgetting the third author, who explained what happens if you ask complicated questions. But let a black hole form from collapse in a pure state and ask simple questions. Well, first of all, since it formed from collapse, the observer at infinity can know how it formed and what the state was. So you should have complete knowledge. And the quantum extremal surface is actually empty in that case.
Oh,
And see, you have access to the complete boundary, and the complete boundary is null homotopic. In these pictures, I assumed you had access to only part of the boundary, like A, and then the quantum extremal surface had to be homologous to A. So, okay, but suppose you have access to the whole boundary. The whole boundary is null homotopic. So the simplest version of your question is to assume you have access to the whole boundary, and therefore the empty surface, the boundary is null homotopic. I mean, that region you have access to, if it's the whole boundary, is null homotopic in the case of a black hole that formed from collapse. So in the simplest version of your question, the quantum extremal surface is just the empty surface.
I see.
And that's consistent with the fact that the simplest version of your question, you assume the black hole formed from a pure state. So the fine-grained entropy should be 0. And an empty extremal surface gives the correct answer. I mean, we can ask other versions of the question to get different answers. The general story is that we always will look for a quantum extremal surface. But if there isn't a bifurcation surface in the space-time, the quantum extremal surface won't be a bifurcation surface, obviously.
I have a simple question.
I'm going to say one more sentence in answer to that last question, though. A lot of experience with this shows that you always land on your feet with sensible answers. I gave a few examples, like strong subadditivity and the secret sharing, the dividing the information among 3 observers at infinity, where we got sensible answers. But I only gave you a tiny taste. There's a lot of experience by now where these things always give sensible answers. Well, I kind of gave one example in answering you, where the black hole formed from collapse from a pure state. And the quantum extremal surface recipe then says that the fine-grained entropy is 0, which is the correct answer. Okay, anyway, let's go on to the next question.
Yeah, I have a simple question. You gave a simple geometric proof of strong subadditivity of entropy using triangle inequality.
Yes.
Then does strong subadditivity of entropy still hold in higher dimension using area?
Yes. Not only that, but essentially the same proof still applies. I drew, if you think about it carefully, in higher dimensions, these curves I've drawn are extreme minimal surfaces of higher dimension. But if you think through carefully how they have to intersect, you'll see that the same proof still applies. So for example, SAB and SBC, suppose we're in 4 dimensions. SAB and SBC are now 2-dimensional, but they intersect on a curve. And that curve still divides them into different regions. And it's still true that this has area bigger than this plus this, or less rather than this plus this. And this has area less than this plus this. So it's not, you wouldn't call it the triangle inequality anymore, but the idea is the same.
Oh, that's very simple.
Yes.
There's a question from Liliana.
Hi, I have a simple question. You were talking about this RT formula in the context of holography.
Yes.
And they use a particular ADS-CFT correspondence, right? But right now, you mentioned there are, after that, there were many developments.
Yeah.
So what is the status now? Is it like general formula that works for every ADS-CFT correspondence, or in which cases it can be applied?
No, well, even at the beginning with the original RT paper, it was general for the ADS-CFT correspondence. In the first decade or so, it was applied in the ADS-CFT correspondence in different examples of that. Now, in the last couple of years, people have learned some fancier things you can do. I don't think a useful, okay. I think the most you might have is that if there's a region at infinity that can be treated classically, and a region in the bulk where gravity is important, you might have some kind of RT formula. That might be too optimistic, but that's the most optimistic you could reasonably be based on what people are doing now, I would say. I think everything that's actually been done fits into what I just said.
Okay. Thank you.
Sure.
And there's a question from Hanul Song.
Does generalized second law hold dynamical properties like non-stationary?
The question was, for a non-stationary black hole, does the generalized second law hold?
Yeah.
Well, for a non-stationary black hole, it holds, but it doesn't go beyond what Beckenstein said, because we proved last time that if the horizon isn't stationary, then the area is increasing. We proved that using properties of Einstein's equations, using the Einstein-Ricciardori-Sachs constraint equation. And if the area term is increasing, then normally the quantum correction is negligible. So just the fact that the horizon is non-stationary means that we don't have to worry about the quantum correction.
Yeah, okay.
The generalized second law is true.
Can I ask one more?
Yes, please.
Yeah. Particle cannot reach each left and right universe, or can particles interacting inside of up and down triangle region in Penrose's diagram?
I had trouble hearing. Could you repeat the question?
Particle can interact in up and down triangle, each other,
Triangles.
up and down.
Oh, these two.
Yeah.
Okay. What do you want to know about them?
Particle can interact in that region.
Well, I'd say what those two regions mean is quite mysterious. So really, what the top and bottom triangles mean is one of the big mysteries in the field. So this geometry describes an entangled state of two worlds. So this triangle describes one world, this triangle describes the other world, but only because they're quantum mechanically entangled, the future and past triangles exist. Well, that's the quantum interpretation. Of course, the classical interpretation is you solve Einstein's equations and the two triangles are there. But when you start interpreting these things in terms of the relation to quantum information theory, the upper and lower triangle exists because the left and right spaces are entangled. And what it means, I'd say, is quite a mystery. Nobody knows what to say about it. I'm not sure if that was responsive to your question, so if not, please ask again.
No, nothing.
Okay, thank you.
There's a new question from Pablo.
Hi. So maybe this is related. The previous days, when you were separating left and right, that was more like inside and outside of the black hole.
Yes.
And today you separated left and right, but never took into account the inside of the black hole. It's more like the asymptotic left and asymptotic right.
Yes. People the subject started with the only interesting division between the inside and outside of the black hole. But you're quite right that in the last decade or so, people have learned to do other things using similar ideas. And as much as I could in this one lecture, I tried to give some introduction to that. There's way more than I've been able to explain.
I see. So I see. Because if I look at this picture that I see right now, if I draw a horizontal line mostly anywhere, there will be 3 regions and one would contain the inside. Maybe it's related to the previous question.
Well, let's actually draw it. So let's draw a generic cut. Now, in the first 2 lectures, I would have told you only about this portion of the cut,
Right.
or this portion, because that portion is the exterior of the black hole as seen by an observer on the left. In neither lecture have I told you anything useful about this region, and I'd say nothing, well, nothing beyond whatever you can learn from classical physics is understood about it.
True, but the entanglement that you described today was between the 2 outside regions, and the entanglement you were describing when you were doing the density matrix, you were tracing over the internal part of the black hole and the previous regions.
Yes, right. Well, morally, you presumably, well, okay. But see, what you just said goes beyond what anybody knows. So one would like to, well, okay. First of all, the Bekenstein-Hawking entropy of a black hole is coarse-grained. It isn't just tracing out. Okay. Yeah. Okay. It represents some kind of averaging over what's behind the horizon. I would say nobody understands exactly what it means. So I'm not going to be able to give you a proper answer.
Okay, thanks. That's more than enough then.
That's what? Didn't hear that.
More than enough then.
Okay.
Thank you.
Jonggi has the next question.
Yeah, thank you for the great lecture. In this lecture, usually you talk about some factorization of Hilbert space, like and right and so on. And if there is a gauge field, can we always consider such factorization? And can we consider the factorized Hilbert space? And is it really essential to consider factorized Hilbert space, or just for simplicity we consider factorized Hilbert space?
Well, I describe it that way for simplicity in the explanations, and because it's hard to do better. Technically in quantum field theory, the Hilbert space doesn't factorize. And the symptom of that is the universal ultraviolet divergence in the entanglement entropy. After all, if the Hilbert space was a product, it would be possible to have a product state with finite entanglement entropy. That's not the situation, or even 0. That's not the situation. The vacuum has divergent entanglement entropy.
Okay.
And every state is like the vacuum at short distances. So the leading divergence in the entanglement entropy is universal for all states. And so technically the tensor product is oversimplified.
Even this eternal black hole case.
Oh no, the eternal black hole case, since the boundaries are disjoint, then that is a tensor product Hilbert space. That was correct. But in all other examples, sorry, to go to another page, I have to close that. So here, the claim that C and D have disjoint Hilbert spaces is oversimplified. What is true, rigorously, is that the state on the full boundary can be reduced to region C or to region D. But the claim that that reduction is a partial trace is oversimplified. And that oversimplification is the reason that there is this universal divergence in the entanglement entropy. You have to be careful, although I don't believe I've made any statements. I've made statements in these 3 lectures that were slightly oversimplified technically, but I do not believe I've made any statements where that led you significantly astray.
Okay, thank you very much.
Sure.
Dongsu has a question.
Well, I mean, you emphasized that the generalized Bekenstein-Hawking entropy is thermodynamic coarse-grained entropy in a certain sense. But in the derivation, you used quantum relative entropy, which is basically fine-grained in a certain sense.
Well, it's fine-grained for the state on the horizon. But, well, okay.
So one, perhaps one can clarify, one can give a sense to the Bekenstein entropy as some sort of fine-grained entropy.
Well, I'd say we made a little bit of progress in that direction. We would like to know in what sense the Bekenstein term A over 4G H bar comes from fine graining something, but we don't know, or coarse graining something. We don't have such an interpretation, but you're correct in pointing out that for the quantum correction to the area, we did have a fine grained interpretation. So we didn't use the relative entropy for the complete generalized entropy, but we used the relative entropy for the quantum correction to the generalized entropy.
Oh,
So see, we didn't have any useful interpretation of the A over 4G term. But then there was a quantum correction to the A over 4G term because of the stress tensor of infalling quantum matter. And we were able, Aaron Wall was able to give a fine-grained interpretation of that. So it's a little bit of progress, I think. Literally, the big part of the Bekenstein-Hawking entropy is a mystery, but the small quantum corrections to it we can describe in a sensible way. That's the best we can do.
Well, let me ask it this way. In the eternal, this two-sided ADS black hole case, if one perturb, then as you said, the area increase, horizon area increase.
It increases if the two parties start manipulating it.
Yes, and then in that case, what is a proper interpretation of that area contribution?
Well, there are two things we can do in this picture. So the area of the extremal surface, which is where the two lines cross, is the entanglement entropy between the two left and right. And that's time independent and completely independent of all these in and outgoing red and blue particles. That's one thing we can do. The other thing
is fine-grained, as I understand correctly.
Now there's something else we can do, which is that we could be an observer on the right, for example, and the observer can make a cut of the horizon, and then we can follow Bekenstein and Hawking, and A over 4G plus the entropy on the cut is some kind of generalized entropy of the black hole as seen by the outside observer. And it obeys a second law. If you move the cut into the future, that will increase, as we proved.
So that can be some sort of fine-grained entropy, or in a sense of entanglement.
Well,
entropy on a certain slice.
Well, it does not have a known interpretation as entanglement entropy. And the fact that it obeys a second law indicates that it's coarse-grained in some way.
Okay.
I will not be able to give satisfactory answers to these questions. Your question is, your question is getting at things we don't understand.
Okay. Well, thanks a lot for the clarification.
Sure.
Mingyu Kim.
Okay. This question is more related to recent development rather than your lecture.
Yes.
But the question is this: the user page curve for the von Neumann entropy is drawn like a graph going up till the page time and going down.
Yes.
But on the other hand, Subrat Raju argued the page curve should be the just constant graph, since we cannot assume that Hilbert space factorize into the degrees of freedom inside black hole and the outside. So I guess if this idea is correct, there is no island in black hole. So could I hear your opinion for this idea?
Well, It's hard to answer the question properly in the context of these lectures because there are many ideas you're alluding to that I didn't explain and can't assume are familiar to the audience. But although Suvrat's ideas are very interesting and I found his paper very stimulating, I think his argument is actually has a problem that he himself pointed out, which is that the Bondi mass apparently can't be measured on a cut of the surface at infinity, a cut at null infinity. However, I think Suvrat's observations are interesting, and in some other way they might be important. I'm pretty sure that the story about the page curve is valid and important. I think that was important progress in understanding the subject.
Okay.
Sure.
Any other questions, comments? Dongsu, you are not raising your hand, are you? Yeah, he forgot to unraise it.
It was.
So may I ask a question?
Yeah, sure. Hands up.
A gravitational system is described by Rich tensor and the Weil tensor, and then the rich part is described by the matter field. But suppose that some gravitational system is described by purely a Weil tensor part, then what is the meaning of the entanglement for such a system?
When you say it's described only by the Weil tensor, you mean
yes.
that the zero?
That is the purely described by gravitational degree of freedom that determined by matter field, but we don't know how to define quantum gravity. So for such system, what is the meaning of entanglement?
Well, we don't know full definition, full answer, but we believe that for example, in the antidissident, okay, this picture can't quite have zero Weil tensor because there's a cosmological constant. But I think the general answer to your question is that even though we don't, for example, completely understand the duality involved in this picture, we believe there is a quantum gravity system in the bulk that's dual to the boundary quantum system. And well, the entanglement entropy is an entanglement between two states of that system. There's too much that isn't understood to get, I mean, you're asking good questions, but there's too much that isn't known for me to give very satisfying answers.
Thank you.
Sure.
I think it's Changyeong.
Yeah. Well, I wonder whether the strength of additivity of RT from the RT formula can explain the entropic gravity idea.
Can explain what?
The entropic gravity idea of Berlin, etc. So I mean, two part together, the entropy is less than the addition of each of them.
Yes.
That idea can be related to the entropic gravity idea.
I don't know how to relate these ideas usefully. So interesting question, but I don't know how to respond to it.
Okay.
Any other questions, comments? If not, Junggi, are you asking question again?
Yes, if there is time.
Maybe last one.
Okay, thank you. So in your lecture note in a few years back, you explained the Lee-Schulder theorem. Is it any give us some nice hint to this black hole information paradox, or it is just nothing to do with this black hole physics?
Well, the Lee-Schulder theorem is the theorem that explains that in ordinary quantum field theory, there's a very high degree of entanglement between two regions. So I do think the Lee-Schulder theorem is important background to the subject we've had today. It had in the last 3 lectures. I mean, so for example, in this picture, the Riesz-Leiter theorem would tell us that states here are completely entangled with states here. But of course, in this particular case, something much more precise is true. They're completely entangled in the thermophile double state. Whereas the Riesz-Leiter theorem would only have given us more general information. So I'd say the Riesz-Leiter theorem is part of the story, certainly. But it only takes you so far because it's so general. I see one more hand up, so maybe we
5분
should.
안에 다시 한번 나와주시죠. 아니, 5분 뒤에 가능합니다. 네, 감사합니다.
Kim Young, are you saying something? No, he was on. So there was one more. Chong, you're up?
Yes. So this generalized second law works for general quantum theory, or this is only for like black holes?
Well, it's for stationary horizons. It's general quantum system in the sense that the quantum field theory, what we discussed was quantum fields in a background spacetime. Quantum fields coupled to general relativity. The quantum fields could be any quantum field theory in curved spacetime. And but then you can ask, is it only valid for black holes? As one of the questioners mentioned yesterday, the discussion also applies to cosmological horizons. It's a little bit more general than black holes, although black holes are the motivating example and perhaps the most exciting example. But in general, the analysis yesterday was, I think, for any stationary horizon.
Okay. I see. Thank you.
Any other questions, comments? Kim Young?
Let me say a few words. On behalf of our Korean audience, I would like to thank you, Professor Witten, for your 3 wonderful lectures.
Thank you.
Your lectures have been and will be strong encouragement for us. As you have advised, we will keep investigating the difference between what is true and why it is true. Thank you again, Edward.
Thank you very much for the kind words. I greatly appreciate them. And I've enjoyed preparing the lectures, and I want to thank KIAS and all of you for the invitation and for the stimulating questions and discussion. And let me wish all health and good fortune to all of you.